In mini lectures 34 and also in mini lecture 35, we're going to look at power for sinusoidal circuits. Electric circuits are built, they are designed to deliver signals, whether it is, and by the way, when we say signal, I'm going to link that to power shortly, to deliver signal, whether it is essentially what's coming out of your electrical outlet because you want to power appliances that you have at your home, or in fact, if you're also looking at from a communication standpoint, you're receiving power from a cell company, you're receiving power in your cell phone. So when we talk signals, the way that companies essentially act on the signal is by measuring power. So when you look at your light bulb and you see 60 watts, it has meaning. There's a certain amount of consumption, power consumption that implies, and you obviously bill for that consumption of power, but the utility company is delivering that power to you, which you are paying for. So power is a really very important part. It is a measure of what's being delivered to a particular system, to a particular load, and it's often what's being charged for, what you're paying for. So today we're going to look at power. We're going to look at what's called the average power. It is the most important power calculations. The next mini lecture, we're going to look at the complex power, which has everything. The complex power essentially gives you all kinds of power informations. And those of you who are electrical engineering students, if you go on into other courses, you will see how this thing plays out in other courses, whether you're a power or an electronic student, if you will. Okay, so let's share screen here. So before I begin here, when we look at power, if any power questions you have, assume you've solved the circuit, okay? So we're going to begin this discussion by assuming you know voltage and current here. So I am going to begin this by showing you. So again, we're talking about sinusoidal power. So we're talking about circuits that are operating in steady state. They have sinusoidal signals. They're on for a long time. And we have one frequency. The typical nomenclature that we have defined for applying the phasor method. So this, the remaining part of this semester, I assume this circuit meet the phasor method requirements that we just talked about right there. In this particular case, we start by assuming, okay, we have it could be an element. It could also be a piece of circuit, basically. The only thing that you probably should know at this point, that it must be a passive element because the current is entering the positive terminal. So I'm applying the passive sign convention in this, okay? So, and I assume, again, in the time domain, I assume that I solve the circuit using mesh or nodal, and I find a voltage across this particular element, that's some magnitude Vm cosine omega t, the frequency of whatever sources are, plus theta, and a current through it, Im cosine omega t plus phi. So in essence, you know that, and if I were to ask you to what would be the phasor representation for this voltage and currents, you would tell me the phasor voltage would be Vm at an angle theta, and you would tell me that the phasor current would be Im at an angle phi, okay? So that's basically what we've been talking about. So what we're going to do, essentially, we're going to calculate what's called the instantaneous power. The instantaneous power is a power at any given time, t. Okay, the instantaneous power, as we know from way back when, power is voltage times current. So I simply multiply the voltage times the current. And then we use this trig identity to express cosine A times cosine B. And we get this to be the instantaneous power. Okay. The instantaneous power has some interest, but it's not the most important part. What I'm going to do right now is take the average power. Okay, the average power over the period, over one period of that signal. So when I do the average power, again, it integrate over one period of the signal here, and I find the average power to be this. This is the most important power calculation in electrical engineering. Okay, it is the power, the watt, the 60 watt for your light bulb. It is the measure of whatever you're being billed for utilities. It is really the most important power. So the unit of the average power is watts. It is the magnitude of the voltage, the magnitude of the current divided by 2 times cosine the angle of the voltage minus the angle of the current. So this is something you need to know, okay, because that is the most important power calculation for sinusoidal circuits, all right? So we're going to zero in on that average power. We're going to look at it for resistor, for capacitor, for inductor, and do an examples and try to look at it in a little bit more details. Okay. So if I have a resistor again, if I put a current in, I'm moving into phasor here. If I put a current IM at an angle phi, then obviously the voltage is the resistance times the current. So you can see that. All right. And then I can calculate the average power. So for resistor, we have 3 formulas for average power when it's for sinusoidal circuit. We have Vm, Im. Again, Vm and Im are the magnitude of the current and voltage. Vm, Im over 2. We could also write it as R times Im squared over 2. We can also type that Vm squared divided by 2R. Okay, this kind of reminds us what we did when we were dealing with DC circuits. Okay, the 2, by the way, has to do with an average value of the voltage and of the current. Okay, so we have 3 alternative formulas. Of course, that previous one works as well. We can always use that one. But when we apply it to a resistor, essentially the current and voltage have the same phase angle because the voltage equals the resistance times the current. So that for the resistor, that cosine theta minus phi, that angle become 0, so the cosine become 1. So that's basically what we're seeing here when we apply it to a resistor. And then we get these alternative formulas that are equivalent, essentially, okay? If we apply it to an inductor, we put a current Im at an angle phi for an inductor. Again, we can apply the impedance for the inductor times the current is equal to voltage. We're talking in phasor. So you can see because J is a complex number in rectangular form, but in polar form, it's 1 at an angle 90. So we can see that when you do that, the voltage is 90 degrees essentially ahead of the current, okay? That's what you see when we do that. So the cosine theta minus phi, that becomes a 90-degree difference. So the cosine is 0. So the average power for an inductor is 0. It makes sense because the inductor doesn't dissipate power. If you remember anything about an inductor, it actually takes in energy at some point and releases it at another point. There is no net loss, so on the average, it dissipates 0 power. Okay, so that actually makes sense, but I wanted to show you that. We can do the same thing for the capacitor. We can put a current Im at an angle phi, except we're multiplying now to get the voltage by the capacitor impedance, 1 divided by j omega c. And we can see that the angle becomes minus 90 degrees, okay, between the voltage and the current. Again, the average power gives you 0, which makes perfect sense for a capacitor. On average, it is dissipating 0 power, okay? So these are things that if I ask you for an average power for any capacitor or inductor, you ought to be able to immediately reach that conclusion and explain why. So a little bit of summary here. We're dealing with these 2 reactive elements for inductors and capacitor. The average power is 0. On the other hand, the instantaneous power is not, okay? We can look at when power is positive for either a capacitor or an inductor, the element, it's actually storing energy. Okay, when power is negative, it's releasing energy. But on the average, essentially, it dissipates no power. Inductors and capacitors are lossless element in the ideal case. Okay, so that's what this is showing here. So average power for inductors and capacitor should immediately, you should be able to conclude that there's, that's 0. All right, so let's look at a basic example here to cement this. And then we'll kind of summarize the average power here. We'll look at it a little bit more detail here, okay? This question is asking, find the average power supplied by the source and the average power dissipated by the passive elements, okay? You should immediately be able to say that the average power by this capacitor is 0 from this discussion we just had. But we can actually show it. If we calculate it, that should play out, okay? So whatever average power this source is producing is going to be dissipated by the 5 ohm resistor. That's essentially what you're going to be seeing here. All right. We're going to solve this using phasors. If you remember about anything about phasors, the phasor method is referenced to cosine. So one of the first thing I'm going to do is convert that 10 sine 2t to cosine. So it will be 10 cosine 2t minus 90 degrees. Okay. That essentially to convert the sine to a cosine. We apply the phasor method based on cosine, not on the sine function. So I'm going to go ahead essentially and go to the phasor domain, which means I calculate the capacitor and impedance, 1 divided by j omega c. My frequency was 2 radians per second. Okay. And then obviously the resistor, it's the resistance, is the impedance. And then I convert my source. I first convert it to cosine function, then convert it to the phasor form. Okay. Once I do that, I can calculate the current for this circuit by taking the voltage divided by the sum of the impedance. And then once I have the current here, I can calculate, I can answer the question actually, but I could calculate voltage if I want to apply the formula the way that I've set it up with. Okay. In this case here, I find that the current is 1.414 at an angle minus 45. Okay. Of course, I can calculate the voltage. I'm trying to formally apply the formula that we just saw at the average power is the magnitude of the voltage, the magnitude of the current divided by 2, cosine the angle of the voltage minus the angle of the current. Okay. So I calculate the voltage for the resistor, 5 times I, and the voltage for the capacitor, minus J5 times the current. Okay. Then I'm in a position to answer the average power for each element, for the source and for the resistor and the capacitor. Remember, for the source, we need to apply the active sign convention, whereas for the capacitor and inductor, we're applying the passive sign convention. All right. So again, the average power is 1/2 the magnitude of the voltage times the magnitude of the current, cosine the angle of the voltage. I'm using the color to remind you of that, minus the angle of the current. Okay. So for the resistor, I just plug this in. I calculate the resistor voltage, the resistor current, and I find 5 watts. Okay. Once, because I know the current, I calculated the voltage, so I can apply the formula. For the capacitor, I know the answer should be 0, but you can show that. Okay, if you know the voltage, you know the current. If I blindly apply the average power formula, I'm going to find that the average power for the capacitor is 0. All right, and for the source, you can expect to find the 5 watts. The same 5 watts the source puts out. Again, the current is satisfying the active sign convention. It's entering the negative terminal, which is what it is. And then we can basically write the power calculation, the average power, and find that it is 5 watts. So average power is conserved. The average power that the source puts out is the average power dissipated in the resistors. In this case, you only have one resistor. Okay. So this introduced the average power, the most important power calculation for sinusoidal circuits. The next lecture, we're going to enlarge this to complex power, which has a whole bunch of important information in it. So let's just do a little bit of drilling down. So this particular lecture and the next lecture is full of notations. And if you become a power student in electrical engineering by any chance, you're going to find that these notations are very important. And many of them has to do with regulation as well. So we look at the average power as 1/2 the magnitude of the voltage, the magnitude of the current, times cosine the angle of the voltage minus the angle of the current. Okay. So we call this 1/2 VMIM, we call it the apparent power. Okay. The apparent power in volt ampere. Okay. And then we call the cosine the angle of the voltage minus the angle of the current. We call it the power factor, PF. Power factor. This is a very important commodity, a very important calculation in the power industry. So what we're saying essentially, the average power, which is the average power is often people call it the real power, the average power that is delivered to a circuit. It's the apparent power multiplied by the power factor. So the apparent power is what you think you're sending to the circuit, but the power factor essentially modulate that. And that makes it very important. All right. So when later on, we'll have a little bit more discussion when we look at the power factor, we can link it to whether the circuit is inductive, capacitive, and that kind of thing. All right. We also can define what's called the effective or RMS value of the voltage, which is VE, which is Vm divided by square root of 2. And also the same thing for the current, we can define as IE is the magnitude of the current divided by square root of 2. All right. So those are things that are pretty common. Again, I'm just giving you some notation so that you are very well armed if you go on to other courses that might be helpful. So the average power is the apparent power multiplied by the power factor. Okay, keep in mind the power factor is always less than or equal to 1. You cannot have a power factor greater than 1 by virtue of the cosine. Okay, so the power factor is always less than or equal. This is why we say the apparent power is the power you think you're setting to the particular element, but the multiplied by the power factor, which is always makes that less. Okay, so let's focus a little bit more. So let's assume we have a particular impedance, so a passive element, and some net impedance R plus JX, okay, some passive circuits, and it has a current Im at an angle phi and a voltage Vm at an angle theta. Clearly, we can state that the ratio of voltage to current must be equal to the impedance of the circuit, the net impedance of the circuit. Okay. All right. So what we end up seeing essentially, if we look at the angle that sits in the cosine, the angle of the voltage minus the angle of the current, if that's positive, we can show that we're dealing with an inductive load. We can show that X is positive in the impedance. Okay. So I can ask you, is the circuit inductive or is the circuit capacitive? Those are all information that flows from the ratio of voltage to current. Okay. If on the other hand, theta minus phi is negative, you can conclude that you're dealing with a capacitive circuit. That means X is negative. So those are important information that are gleaned from looking at these voltage and current relationship. Okay. So you're going to hear also, again, if you continue electrical connection, you're going to hear the term lagging and leading. When we talk about power factor lagging and power factor leading, we are looking at the relationship between the angle of the current and the angle of the voltage. Okay, so when the angle of the current is larger than the angle of the voltage, we say that the power factor is leading. The current leads the voltage. Now we are looking at phase angle between minus 180 and 180. So we don't want to see phase angle of 275 or minus 355. So it has to be within that range of minus 180 to 180. So we say that when the angle of the voltage, when the angle of the current is larger than the angle of the voltage, we say that the power factor is leading. And when the angle of the current is less than the angle of the voltage, we say it's lagging. Okay, so that also you can connect also to, you can also connect essentially being inductive and being capacitive. And so in this particular case here, so if you look back here, when the angle of the voltage is larger than the angle of the current, we have an inductive load. Okay, we have an inductive load and the power factor is lagging. So the power factor lagging means we have an inductive load. And when the angle of the voltage is less than the angle of the current, you have a capacitive load and you have a leading power factor. Okay, so that's kind of wrap up this here. And we're going to look at it from a different point of view, from a point of view of the complex power in the next mini lecture. And if time permits in the course, we're going to conclude with an example to show you how this all ties here. So I'm going to go to the document camera and summarize a little bit of that information here. So give me a minute here. Okay, so we started by this thing by assuming you can assume some elements, okay? Some elements that has a current Im cosine omega t plus phi, and it has a voltage across it Vm cosine omega t plus theta. So essentially, I'm basically giving you two different magnitude, and this is some passive circuit. Okay, so that's what we have here, and you know it's passive because the current is coming in the positive terminal of the voltage. Okay, so we started this, and we essentially, so in this circuit, we can easily show it as in phasor. We can easily show it as the current is Im at an angle phi, and the voltage here is Vm at an angle theta. Okay, that's essentially the circuit in phasor. Okay, all right, that's what we have. And then we proceeded to define the most important power calculation, the average power. Again, some people call it the real power. Okay, the average power is 1/2 the magnitude of the voltage, the magnitude of the current, cosine the angle of the voltage minus that of the current. And the units of the average power is watt. All right, the most important calculation, it's what utilities company charge you for. Any kind of delivery of signal usually include a power calculation for which you often are charged for. All right, so that's your first thing here, and that's probably the most important calculation. Then we define the apparent power. The apparent power would define it as 1/2 Vm Im, and the units are volt ampere. So these are things that I can ask you after solving a circuit, volt amperes. Okay, then we define the power factor. We call it PF as cosine the angle of the voltage minus that of the current. Power factor is always less than or equal to 1. Okay. Power factor does not have units. Power factor doesn't have, it's just that. Okay. So these are important things. And then finally, one of the questions you kind of basically have to remember is you're going to be able to qualify the power factor, the PF. Qualify the PF. Okay. Qualify the PF, that is when theta is greater than phi. Okay. This is an inductive load. It also means that the power factor is lagging. Okay. When the angle of the voltage is larger than the angle of the current, you can infer you're dealing with an inductive load. This is an inductive load, and the power factor is lagging. On the other hand, when theta is less than phi, you're dealing with a capacitive load. Capacitive circuit, and the power factor is leading. Okay. So this is kind of a good summary of what we're talking about. Again, all of that comes after we solve mesh and nodal for a particular circuit. Okay, but these are notations that you need to know. Again, the average power is the most important power calculation. The apparent power, the power factor is a very important calculation, particularly for the power industry. And if you maybe when I do some example, I might relate to you how that's important here. The apparent power is what you think you're sending. You think you're sending to a particular circuit, but multiplied by the power factor becomes a real power that you send into that particular circuit. And again, we can glean some information about the power factor from the power factor or the angle in the power factor. We can glean some information about whether the circuit is inductive or capacitive. Okay, thank you.